In part 2 of our discussion of Chapter 6, we are going to turn our attention to the chemical mechanisms by which enzymes facilitate catalysis. So here we will be looking at the actual chemistry and the chemical paths that enzymes use to convert a substrate into product. All catalysts, enzymes as well as chemical catalysts, employ certain chemical routes that lead to rate enhancements. With respect to the comparison just made, the enzyme versus the chemical catalyst, we're going to see very similar approaches, though enzymes tend to produce greater rate enhancements due to additional effects. Think about the proximity effect and ES complex destabilization, strategies like that we talked about last time. Here, our focus is on the chemistry itself. So the four major types of catalytic mechanisms with respect to the chemistry that we're going to talk about are acid-base catalysis, covalent catalysis, metal ion catalysis, and the proximity and orientation effects that we have talked about, not in as much detail as we will here, but we have talked about these. Now, one thing I want to point out going in, most enzymes are going to utilize multiple types of covalent or multiple types of catalytic mechanisms. So you're not going to see enzymes, for the most part, there are exceptions, I will show you some of these exceptions, but for the most part, enzymes are not going to use just one type. So you're going to see enzymes use some acid-base catalysis, some covalent catalysis, some metal catalysis, all in one single enzymatic cycle. So this is very unique in that you'll see it is not uncommon for chemical catalysts to just rely on one type of chemistry. Enzymes, on the other hand, take advantage of the full toolbox. If you think about these catalytic mechanistic routes, these types of chemistries as being tools within a larger toolbox, the enzyme sort of pulls what it needs in order to elicit the greatest catalytic rate enhancement. The first type of chemistry that we will look at here is that of acid-base catalysis. So before I go any further, let me remind you, in order for any of these mechanisms to be viewed as catalytically relevant, we are looking at something that ultimately leads to stabilization of the transition state, which is going to minimize the activation energy. So here, when we talk about acid-base chemistry, what we should really be thinking about is the fact that acid-base chemistry, this implies transfer of protons to or from something to something else. And if this is going to be something that is catalytically useful, this implies that the transfer of protons to or from the substrate or intermediate is going to ultimately lead to transition state stabilization. So remember that here, that it always is going to come back to the stabilization of that transition state. Now, when we think about acid-base chemistry, we have multiple options within the side chain functional groups inherent to the standard 20 amino acids. So you have your carboxylic acid-based functional groups in glutamic and aspartic acids. Okay, you've got your amines in lysine and arginine. You've got a thiol in cysteine. You've got your imidazole in histine, your alcohol in serine, and your phenol in tyrosine. Now, you'll see in each case here you have the general acid form, so the protonated form. Here you have something that can function as a proton donor or an acid. Then you have the deprotonated form on the right-hand side, the base form. You're going to notice that hopefully, if you recall any of the pKa's from previous chapters, that at physiologic pH, some of these functional groups are going to be better acid-base catalysts than others. Arginine, given its side chain pK of about 12, is going to be a very poor acid at physiologic pH. Imidazole, on the other hand, the side chain of histidine, has a pK of about 6. So at pH 7, it can pretty readily function as a proton donor or acceptor. And so you'll see histidine very commonly show up as a catalytic active site residue. There are cases where your glutamic acid and aspartic acid side chains will experience perturbed pKa's and actually be able to function as a proton donor more readily near physiologic pH. But that is not the norm. That requires active site tuning, the manipulation of local chemical conditions around those functional groups. So just be aware of that. When we think about acid-base chemistry occurring, the typical chemistry student is going to think, oh, okay, acid chemistry is going to occur better at lower pH. Basic chemistry will occur better at higher pH, more alkaline pH. So in this class, we are talking about biochemistry. And so we have to think about acid-base chemistry through the lens of physiologic conditions. And what that means is we need acid-base chemistry to occur under neutral pH conditions. So that brings up a big question. Under neutral pH conditions, where is the base, where is the proton coming from to do acid-base chemistry? Because neutral conditions would not favor a whole lot of proton floating around or a whole lot of base. They are by definition neutral. So now, let's think about what this means here. So generally, we have two overall classifications for acid-base chemistry. We have specific acid-base chemistry, or specific acid-base catalysis, where the proton in this form would be a hydronium, or the hydroxide comes from the surrounding solution. So in order for specific acid-base chemistry to occur, you have to manipulate the solution pH. So as an example here, this reaction that is shown here, this is the hydrolysis. This reaction is a hydrolysis reaction that converts para-nitrophenyl acetate. That's what this is. This is, again, para-nitrophenyl acetate. It's going to react with water. Water is going to come in and hydrolyze this ester linkage here to give acetate and the resulting chromophoric product. So I refer to this as a chromophoric product. This is actually just nitrophenol, I should say. But the conversion of the reactant here to the product yields a change in absorbance properties. And so you can actually follow this reaction by a change in absorbance at a particular wavelength. So this has been used as a probe pretty widely to study different hydrolysis reactions. Now, in a specific base mechanism, para-nitrophenyl acetate is going to be hydrolyzed by hydroxides that are present free in solution. So what that means is that this reaction can only occur as shown under basic pH conditions, elevated pH conditions. And so what's going to happen is you're going to see the hydroxide is going to undergo nucleophilic attack on the electrophilic carbon to form the tetrahedral intermediate that ultimately decomposes into the products. So that would be the specific base mechanism. Now, in order for this to happen, you need elevated pH conditions. You need basic pHs. That is not how we live. We live under neutral conditions, neutral pHs, pHs in the ballpark of 7, 7.5, something like that. So what this means is that this specific base mechanism is not always compatible with physiologic reactions. So the alternative here is general acid-base catalysis. And what this refers to are proton transfers that are mediated by weak acids and bases other than water. So this is a very broad term, but the weak acids and bases other than water that we are interested in here are the amino acid side chain functional groups. So here, as shown in the general base mechanism, the imidazole side chain of histidine actually reaches over, grabs a proton off of a water molecule, which then generates a hydroxide that can attack via nucleophilic attack the electrophilic carbon, and the same chemistry occurs. Now, the general base mechanism is possible under neutral pH conditions. pH 7 or 7.5 is high enough to populate a significant population of deprotonated histidine, which can function as a proton acceptor and lead to what is called water activation. So basically what is happening is by grabbing a proton off of a water, where under neutral pH conditions, water is everywhere, we are locally generating a hydroxide that can function as our nucleophile here. So we don't need extremes of pH in order for this reaction to occur if we have a functional group that can function as a weak acid or base and do what I have described here. So specific acid-base catalysis requires extremes of pH, or at least non-physiologic pH, to occur because the proton or the base comes from the bulk solution that surrounds. Whereas in the general base mechanism, or general acid mechanism for that matter, the acid or the base, the proton or the hydroxide, is generated by a weak acid or base, most often associated with the enzyme itself. The use of functional groups derived from your common 20 amino acids to do acid-base chemistry at an enzyme active site also means that the activity, the overall enzymatic activity of the enzyme in question here is going to depend upon the pH. Remember, each of your amino acids that can do acid-base chemistry are defined by some pKa value. So what that means is that as you vary the pH, you're going to see changes in the protonation states of those amino acids at the enzyme active site, which may either increase or decrease overall catalysis if you happen to alter something that is of catalytic relevance, of course. Now, if we look over here, what I want to show you is an example of this. So here we have enzyme catalytic rate. So this is something that we're going to refer to later as the initial velocity, and I'll explain later why that is, but just think about this as enzymatic rate or catalytic rate as a function of pH. So what you're going to see is that for many enzymes, you're going to have a bell curve shaped behavior. So here, what you should see is that at low pHs you have lowered catalytic rates, but as you increase the pH, you're going to reach some point where you have maximum catalytic behavior, maximum activity. As you keep on increasing the pH, it's going to sort of drop off. Now remember, the side chains of aspartic acid, glutamic acid, histidine, cysteine, tyrosine, lysine, they all have pKa values that are in or near the physiologic pH range. But in this particular case, we see a maximum around 7. So I'm going to look at that and I'm going to say, oh, that's really interesting because histidine has a pKa, the side chain has a pKa of about 6. So theoretically, what we would be seeing here is a change in the distribution of protonated histidine versus deprotonated histidine. So at very low pHs, perhaps all of your histidine is protonated, but as you approach the pH or the pKa of histidine and reach some value nearby it, you have a mixture of protonated and deprotonated histidine, and that is what maybe leads to optimal catalysis. And then as you keep on raising the pH, not only would you possibly denature the enzyme, but you would also shift the protonation state of that histidine towards being more deprotonated. And so I would probably look at this maximum and infer what I just said. So what you're going to see is that the maximum in a bell-shaped curve like this, where we have this is what we would refer to as a pH rate profile plot. This is going to tell you something about the identity of amino acids at the enzyme active site that are of catalytic relevance. So here the maximum is around 7, which implies that you have a histidine that is necessary for catalysis. But let's say that this was shifted to 3 or 4. There, you might infer that you have an aspartic acid or glutamic acid that is necessary for catalysis. Or let's say this is shifted to even, say, 10. There you might conclude that you have a lysine that is of particular importance. One thing to take note of, though, is that first, the pKa of any acid-base group can vary based on the local microenvironment. So you may find a deprotonated guanidine at, say, pH 9, even though it doesn't normally live that way. In some cases, it can due to the local microenvironment. Okay, so this plot is very important, and it can tell you a lot about, or at least provide clues to the identities of amino acids essential for acid-base chemistry that is relevant to overall catalytic function. So you should be able to look at a plot like this and say something about amino acids that could be contributing to catalysis. Now we're going to turn our attention to a well-characterized example of an enzyme that only uses acid-base chemistry to facilitate catalysis. The enzyme here that we're going to look at is ribonuclease A, or RNase A for short. RNase A is a digestive enzyme that is secreted by the pancreas into the small intestine, where it hydrolyzes RNA to its component nucleotides. So RNase A has been pretty well characterized, and it is known that there are two ionizable residues with pKa values of 5.4 and 6.4. As you'll see in a moment, these are both going to be histine residues, where one of them has a very mild perturbation in its pKa. Before I actually walk through the mechanism, I want to show you the structure of ribonuclease A. So you'll see here that there's some beta structure as well as some alpha structure here. But I want to sort of hone in. These two histine residues here, these are the catalytic histines that we're going to talk about in a moment. Now, I'm showing you this because what I want you to see is that first, they're right next to each other, but also, if I show you a surface view with the electrostatics really highlighted, what you're going to see is that there's a long sort of channel that sits here, or a binding cleft, as we could also refer to it. And overall, this cleft has, you'll see here, a lot of blue. Blue here refers to positive charge. So there's a lot of positive charge through here. And if I go back out, you'll see across this cleft, a histine sort of sits on the bottom, another histine sits up top. So you can imagine the substrate of RNase A nucleic acid, which is very polyanionic, very negatively charged, could easily sit across this binding cleft, could interact via electrostatics, complementary electrostatics very well. The positive charge of the enzyme would stabilize interactions with the negatively charged DNA, and because it's a polymer, in the extended form would sort of sit across this channel as a whole, which would then position those two histidines to sort of sit on either side of the nucleic acid. Okay, so now that you've had sort of a view of the structure and the positioning of these histines relative to the substrate, let's look at the actual mechanism. So what you're going to see is an RNA substrate is going to bind across that channel. I just showed you where that is. So now let's actually label things. So you have an RNA. On the bottom is histine 119. On the top, histidine 12. So what I want to point you to here is that histine 119 at the beginning of the catalytic cycle is protonated. It is protonated. So this is likely the histine that has a pKa of 6.4. It has a slightly higher pKa, which is going to keep it protonated more of the time at neutral pH. Hist 12, on the other hand, is going to have a lowered pKa of 5.4. So it's going to be deprotonated at the start of the catalytic cycle. This is going to be very, very important, because the first thing that's going to happen is this hist 12 is going to lean over to the 2' hydroxyl of your bound RNA and grab a proton off of that 2' hydroxyl to generate the oxyanion. So the O-, the negatively charged oxygen atom, is then going to turn and undergo nucleophilic attack on the electrophilic phosphorus that is present in the sugar phosphate backbone here. Okay, so this is important because what's going to happen at that point is you're going to see cleavage of the backbone. That's going to occur right here. So oxygen comes in, attacks that phosphorus. This phosphorus-oxygen linkage gets broken. And so now you have fragmented the RNA into two parts. Okay, so here, this lower half, this other fragment, is free to leave. But you are still left with an intermediate species, a 2', 3' cyclic nucleotide structure. So we can't just let this go on out into the world. We have to do something with it. So what's going to happen here? Well, at this stage, what I didn't tell you before was that as part of the leaving group strategy, a proton was removed from His 119. So this oxygen picked up this, this proton. And so in this next step, you'll see the protonation states are flipped relative to where they started. So His 119 at this stage is going to function as a general base catalyst. So what it's going to do is reach over, grab a proton from a water molecule to then generate the hydroxide. So this is an example of water activation. That hydroxide can then undergo nucleophilic attack on the cyclic intermediate, and in opening up that cyclic intermediate, the 2' hydroxyl group, or at this stage 2' oxygen, is going to reach over, grab a proton from His 12, and everything is now sort of reset. You have cleaved the cyclic intermediate, it is free to go, and you have also reset the protonation states of these histine residues so that you can come around and do the whole thing again. Now, what I want to note here, this is a chemical mechanism that is facilitated entirely by acid-base chemistry. So if you vary the pH, maybe you lower the pH or you raise the pH, RNase A is going to be very sensitive to changes in the pH because you have two histidines both using acid-base chemistry to fulfill their part of catalysis overall. And so if you change the distribution of protonation states, you may harm, or rather inhibit, disrupt, slow down catalysis as a whole. Another thing to take note of here is that there are no covalent intermediates. So at any step in the catalytic pathway here, if you were to stop the reaction, you would be able to separate substrate from product, or substrate from enzyme, because the enzyme at no point in the mechanism becomes covalently linked to the enzyme. You'll see examples of this later where this does occur. Covalent catalysis is the next example that we're going to look at. And here, covalent catalysis is going to lead to an acceleration of your reaction rate through the transient formation of an enzyme substrate covalent bond. So you are covalently linking your enzyme to your substrate or your intermediate. Now, the side chains of the amino acids in proteins offer a variety of nucleophilic centers for catalysis and include amines, carboxylates, aryl groups, alkyl hydroxyls, imidazoles, thiols. All of these groups readily attack electrophilic centers of substrates and form covalently bound enzyme substrate intermediate complexes. Your typical electrophilic centers in substrates are going to include phosphoryl groups, acyl groups, glycosyl groups. Recall that your electrophiles must include groups that contain an unfilled valence electron shell. They are positively charged or contain some electronegative element. This is going to be important because it either leads to the formation of more or less stable covalent bonds. And the more easily that the covalent bond itself can decompose, the better the reaction is going to be in terms of efficiency in those final steps of that catalytic cycle. Because, I'm saying this because you don't want to form a covalent bond that is so stable that you can never break it. You need, for any covalent bonds that are formed throughout an enzymatic mechanism, to be transient. You have to form them, but you also have to be able to pretty readily break them in order to release your product and cycle through additional rounds of catalysis. So in this figure that I'm showing you, I've highlighted the phosphoryl option, the acyl option, as well as the glycosyl option. In all cases, you have an electrophilic center, whether it be your phosphorus, your carbonyl carbon, or in this case, though we haven't talked about it, your anomeric carbon in a monosaccharide. In all cases, you're going to have a nucleophile, something that is electron-rich, attack, and ultimately lead to a covalent complex. So this is important, but remember that the covalent bond itself must be transient. We must be able to readily break it so that we can keep on cycling through the enzyme mechanism and then move on to additional substrates and keep on going. So pH is also relevant here because many of your nucleophiles, at least nucleophiles that may be derived from the functional groups in the 20 amino acids, may not, when protonated, be readily nucleophilic. A very good example of this is an alcohol. On its own, an alcohol is not the best of nucleophiles, but can, under certain conditions, deprotonate to generate an oxyanion species, which is a great nucleophile. When we talk about the example of the serine proteases in this class, you're going to see that there's an active site serine, which must first be activated by a nearby catalytic residue to generate an oxyanion that can facilitate, can do nucleophilic chemistry. So in cases like the alcohol, you may need some activation step before the actual nucleophilic attack. The sulfhydryl group of cysteine is another example. The primary amine of lysine is also a great example where their deprotonated lysine can undergo nucleophilic attack to form shift base intermediates. That's something that, because of the high pKa of lysine, may require an enzyme that has a very specific polarity in the local microenvironment around that lysine, that side chain primary amine, in order to encourage the deprotonated amine that can do nucleophilic chemistry. So I'm telling you this because what I want you to see in really all cases except for histidine shown at the bottom is that in order to generate that nucleophile, there may be some additional step that occurs before the nucleophilic attack that is responsible for really generating the nucleophile in the first place. The next catalytic route that we will talk about is metal ion catalysis. And before I even say anything, what I want you to go ahead and understand is that I am not covering this in any way that should be interpreted as comprehensive. This is meant as an introduction. Metal ions, are capable of a very broad range of chemistries that are, again, very broad. So here, I just want to generally introduce you to some overall features of metal ion catalysis and not really make you experts on metal ion catalysis because this is a whole field. And so I don't expect that you're going to be experts here. Now, having said that, enzymes will interact with metals in different ways that really generally come down to the strength of interaction. So if an enzyme binds a metal very tightly, you may see that the metal cannot easily be stripped out. It doesn't easily dissociate. So that would be a very high affinity interaction. In some cases, this may be as a consequence of needing the metal ion to support structure, overall three-dimensional structure. Think about the example of the zinc finger motif. That's an example, a structural motif that is stabilized by metal binding. In other cases, maybe it's for other reasons, but whatever the reason, if the metal is bound very tightly to the enzyme, we would refer to the enzyme then as a metalloenzyme. And in some cases, you'll see that the metal binds very tightly. It's not necessary for overall structural maintenance, but it is necessary for catalysis. Whether it be structure or function, the very tightly bound metal dictates that we call this a metalloenzyme complex. In other cases, enzymes that bind metals more weakly, perhaps as a in a way that is similar to like a co-substrate, so it more or less binds with the substrate and dissociates with the substrate. That would be something that we would refer to as metal activated. So in this case, the metal binds much more weakly than in the metalloenzyme case. In either case, the metal activated or metalloenzyme case, we can see that the metal can act as an electrophilic catalyst. So it may stabilize increased electron density. So if you have accumulated negative charge in a transition state, you can see your metal nearby helps to neutralize that overall negative charge and stabilize the transition state. Or conversely, you may see other interactions I'll tell you about on the next slide. So the example here that I'm showing you is the first step of the thermolysin reaction. So thermolysin is a protease. It digests, eats up other proteins. So here, this is a very interesting example because in that first step, what you see is a conversion of an sp2 hybridized carbon, a carbonyl carbon, into a tetrahedral sp3 hybridized carbon. I'm not talking about how this is occurring just yet. I'm talking about the role of the metal here. So first, you're going to see a zinc metal ion bound nearby. That is going to interact with that negatively charged oxygen. It helps to stabilize the positioning of the substrate, and that's great. But its role really shines in the transition state. So that tetrahedral carbon also converts the double bonded oxygen into a single bonded oxyanionic species. The negatively charged oxyanion is not very stable. So in order to stabilize it, the zinc ion interacts with that negative charge. And this is an example of metal ion shielding. It helps to stabilize or shield that accumulated negative charge, where because this is not stable, you can imagine it's relatively high energy. And so by interaction in this way, stabilizing the transition state, we are lowering the activation energy barrier through transition state stabilization. Overall, metal ions are going to contribute to catalysis in three major ways. So the first way here is simply binding to substrates in order to orient them for reaction. So you can imagine a situation where your metal ion interacts with the substrate and helps to position it adjacent to catalytic functional groups that are present elsewhere in the active site. So the metal ion can function to help to orient everybody properly for catalysis. The next major route is through a direct role in catalysis via redox chemistry. So many metals, think iron, cobalt, nickel, copper. These are metals that can pretty readily cycle between oxidation states. So they are capable of participating in oxidation reduction reactions wherein the substrate is modified as well as we go through the reaction cycle. The last route here I've already given you an example of in the case of thermolysin, electrostatic stabilization, or rather shielding of negatively charged transition states. So the accumulation of negative charge in the transition state. So these are the three major ways that you'll see metals participate in catalysis. An example of a metalloenzyme that is particularly relevant to this class is that of carbonic anhydrase. When we talked about hemoglobin and the movement of hemoglobin between lungs and muscle tissue, if you recall, that was accompanied by the conversion of CO2 into bicarbonate by the enzyme carbonic anhydrase. So you have heard about carbonic anhydrase in Chapter 5. Now here we're actually going to talk about it for a moment, very briefly, but enough to really introduce it as a metalloenzyme. So carbonic anhydrase, it is a zinc metalloenzyme. It is necessary for the conversion of CO2 into bicarbonate so that you can move that bicarbonate solubly through the blood from muscle to lungs, where it is converted back into carbon dioxide, and you can just exhale it. So carbonic anhydrase is a pretty cool enzyme. And if you look at its structure, what you're going to see is that there is a zinc ion that is right at the core of the active site, but it's about 15 angstroms separated from the surface of the protein. There's actually a binding cleft that sort of leads down a tunnel, a 15 angstrom deep tunnel, where the zinc lives. So when we start out the catalytic cycle, you're going to see that zinc coordinated by 3 histidine residues. Zinc tends to like to be in a square planar geometry, and so you have 3 histidine residues that are going to chelate it and sort of hold it in place. That's what you're seeing down here in the structure. So this is something that is also species dependent, whether it be a cysteine or a histine. So here you have cysteine, cysteine, histine, but in other organisms it's all histine, so that depends upon the species, but the result is the same. Doesn't really matter. The result is the same. The zinc is held in place. It is coordinated as shown. So when we start the reaction cycle, there's a water that is bound to that zinc, and this gives the square planar geometry. Now, it's interesting here because the zinc, what it actually does through interaction with the water is it polarizes that water. It actually reduces the pKa of that water fairly significantly. So normally, water is going to have a defined pKa, but the interaction with the zinc actually drops the pKa to about 7, which is quite a bit lower. And basically what it does is it encourages deprotonation of that water. So through interaction with the zinc, you see polarization of the water. This is a consequence of a lowered pKa for the water. And then at neutral pH, you see loss of a proton from the water to now leave the hydroxide. So the hydroxide at this stage is still coordinated to the metal ion. Now, a carbon dioxide is going to diffuse into that channel and diffuse down that 15 angstrom deep channel to ultimately hit the active site. So here, this is actually a CO2 shown in this structure. We can't resolve the water here. It is there, but this is the incoming CO2 to that zinc. Now, what's going to happen? So the CO2 is going to come in. Remember, CO2 itself is fairly nonpolar, but this is because you have 2 dipole moments in equal and opposite directions. So this oxygen is pulling electrons away from the carbon, so is this one. So the dipole moments actually cancel out to give an overall nonpolar molecule. But this carbon is very electrophilic because those electrons are all being pulled away. So the hydroxyl group, or hydroxide, can actually undergo attack on that electrophilic carbon, and now we have bicarbonate. So at this stage, bicarbonate can dissociate and leave that channel, and it's moving on its merry way. And a new water molecule can come in and reset the whole thing to do it again. Now, one thing that is interesting here, in this very first step, I told you that a proton is produced, but I didn't really tell you where it goes. If you think back to hemoglobin, you should think, oh, okay, hemoglobin is going to pick that up and it's going to stabilize the T state as things move back to lungs. Cool. But how does this proton actually get out of the channel? This is a very interesting thing, because if you think about proton, it's not actually going to exist as a proton. First, it'll exist as soon as you form it. This proton is kicked off. It's going to be picked up by a water molecule to form a hydronium ion. But in reality, that proton is actually shuttled to the enzyme surface through multiple shuttle residues. So think, histines that are sort of scattered from this point to the surface. So there's going to be sort of a proton shuttle system that moves the proton from here to the enzyme surface, where it can then be picked up by a water to give your hydronium. So this proton, it's not left just to go wherever it wants to go. It is directed through this proton shuttle network that moves it from one place to another. The last important mechanistic route that enzymes use is less chemistry and more substrate positioning. So proximity and orientation effects. As we talked about last time, reactants, in order for reactants to produce product, they must collide in a productive orientation such that you form product. And when I say productive orientation, what I mean is they have to collide such that really orbitals are in alignment, or at minimum, functional groups that are reactive are going to hit each other in such a way that chemistry can occur. So this is important because not all collisions are productive collisions. So as an example, and I gave you a version of this last time, but as another example, let's look at the case of paraphenyl acetate, paranitrophenyl acetate. So here, I told you that the nitrophenyl group, so this group here, upon hydrolysis of the ester linkage, undergoes a change in absorbance properties. So you can easily watch this, and this is, you can pop it into a UV vis spectrophotometer and watch your reaction go. So here, this is a different form of the previous example that I gave you earlier. When I was talking about general versus specific acid-base chemistry, I was speaking in terms of hydroxide. But here, the imidazole of a histine can actually function, can react on its own. It doesn't do this in the example related to enzymes, but here you just have free imidazole and free paranitrophenyl acetate. In this case, the imidazole can undergo nucleophilic attack on the carbonyl carbon to form the N-acetyl imidazolium product, as well as your paranitrophenolate ion. And so this can occur just fine. And this reaction, as shown, is going to be dependent upon the concentration of reactants. So if you increase the concentration of imidazole, the reaction should go faster. Likewise, if you increase the concentration of paranitrophenyl acetate, the reaction should go faster. If you increase the concentration, what you're doing is increasing the frequency of collisions, which also increases the frequency, or rather the likelihood, of productive collisions. So here, as shown, you are dependent upon the reactant concentration. Now let's look at another version of this. Let's actually link them together. Let's take our reactive ester and link it to that imidazole group. Now, when we do this, due to proximity, here, remember, last time we talked about an example of this where you had a linker. You still have flexibility. There's no conjugation in here, no double bonds, nothing like that to keep this in place. So it still sort of freely rotates. But because they are tethered together, the likelihood of productive collision between the imidazole group and the ester group goes up significantly. And when you do this, when the imidazole is covalently attached to the reactant as shown, you're going to see a 24-fold increase in the reaction rate. So this reaction overall, the production of your product here, occurs 24 times faster than when they are not linked. So this is more or less what enzymes do. They hold your substrate in place adjacent to an enzyme active site functional group that is going to react, and by positioning two substrates, or rather two reactive groups next to each other, you are increasing, simply by proximity and orientation, the overall rate of reaction. You are increasing the likelihood of productive collision when bound to the active site. As an extension to the idea of proximity and orientation effects in catalysis, there is a concept that is referred to as orbital steering that is very central to this overall discussion. Orbital steering, what it proposes is that in order for catalysis to properly occur, this productive collision idea that I've been talking about, in order for this to hold, the collision must orient orbitals in alignment such that you maximize the likelihood of orbital overlap upon collision. So what this would imply is that molecules that collide in such a way that their orbitals are not in alignment do not ultimately lead to the formation of product. You need to collide in such a way that the orbitals are all in alignment, and then you can form or break your covalent bonds as you wish to do. In an SN2 reaction, a nucleophilic substitution reaction, type 2, the incoming nucleophile is going to optimally attack its target along the direction that is opposite to that of the bond of the leaving group. So here, you have an incoming group here. It's attacking along the same directionality, it's along the direction that is opposite to the original substituent, such that ultimately you're going to come in here and you're going to have a transition state that has both your leaving group and your incoming nucleophile attached, but ultimately your leaving group is going to leave and your incoming group now is covalently attached via orbital overlap. So here, to restate, the incoming nucleophile is going to optimally attack its target along the direction that is opposite to that of the bond of the leaving group. So this is important because reacting atoms whose approaches deviate by as little as 10 degrees from this optimum direction are going to significantly less active. So activity goes down when you change the angle of attack. So the angle at which the Y atom here approaches your carbon, if you deviate by as little as 10 degrees, you can see very significant losses in catalytic activity. It is actually estimated that by properly orienting substrates, you can increase a reaction rate by a factor of up to about 100, just by proximity and orientation effects. This is really relevant because this is exactly what enzymes do. They bind to substrate, hold it in position such that it is oriented adjacent to catalytic functional groups, and you maximize the likelihood for productive collision leading to maximal orbital overlap. So this has been a discussion of basically the chemistry that enzymes use to stabilize the transition state and ultimately enact these really large rate enhancements that are associated with enzymes. We have focused on here the chemistry, the general catalytic strategies that are used: acid-base chemistry, covalent chemistry, metal-related chemistry, and then proximity and orientation effects, which are all sort of come together to give you the overall rate enhancement. Now, I do want to really highlight that it is rare to see enzymes that use just one, or even two of these overall chemical strategies. What I want to highlight is that, the case of RNase A, that's rare. But even in the case of RNase A, you saw only acid-base chemistry. But what you didn't see was that the substrate, the RNA, was bound adjacent to your reactive imidazole functional groups that are inherent to the histine side chain. So that positioning, that is proximity and orientation. So even in the simple case of RNase A, you had two different types of strategies in play. So what I really just want you to understand is that usually it's not going to be so black and white. You're not going to have just one type of chemistry and then, proximity effects or something like that. Usually you're going to see maybe an acid-base step followed by a covalent chemistry step followed by something else. So you're going to see a mix, and what I want you to think about this as is really what we just talked about. This is your toolbox. We have developed the toolbox of common chemistries used in enzyme catalysis. Next time, we're going to turn our attention to more of the functional descriptions of enzymes. We're actually going to look at enzyme kinetics and inhibition of enzymes. You're going to see that when we develop inhibitors, usually we're going to take advantage of the chemistries that are found in the active site. We're going to try to maybe overstabilize an intermediate or something like that. So tune in part 3 for that.